Greetings to all the viewers. Now we are continuing with the natural products called alkaloids in that strychnine taken into the consideration in the earlier session. Biosynthesis, its significance, occurrence, everything got completed. All are available at the channel called the World of Competitive Chemistry. Any kind of your examination, your preparation towards the examination pertaining to chemistry, all the content is available at the channel called World of Competitive Chemistry. So let me continue with these natural products where strychnine topic taken into the consideration. Their laboratory synthesis is going to be discussed now. Laboratory synthesis of strychnine to be started with indole alkaloid with the side chain of dimethoxybenzene, right? So here, strychnine was one of the most complex synthetic pathway in the organic chemistry, being it is a polyannular system. Here, strychnine synthesis in the laboratory is somewhat complicated in nature. It is the complex synthetic pathway. It was first successfully achieved in the year 1954 by Robert Burns Woodward. He is the scientist accomplished successfully laboratory synthesis of the strychnine. In order to achieve this synthesis, the starting material could be indole, Fischer-indole synthesis type of reaction is accompanied over there. Indole containing side chain benzene with the dimethoxy functionality is the precursor that to be treated with formaldehyde. This is HCHO is called formaldehyde, right? N-comma and dimethylamine can be taken. One is formaldehyde, another is N-comma and dimethylamine are supposed to be treated. Here the formation of CH2NMe2 is possible. This is the kind of methodology resembles with Fischer-indole synthesis, right? So here this CH2N comma and dimethyl amine will be originated. Here methylation is taking place. So this methylation carried later on nitrile group introduced later on. Lithium aluminium hydride is also operated. So with that, what happens? This is the side chain wherever present. That side chain will be the side chain with the one carbonatom will be extended to two carbonatoms containing terminal NH2 functionality. What happened actually, what chemistry involved in this? Methyl iodide when operated that performed methylation upon this nitrogen so that a quaternary ammonium iodide will be generated. Hoffman degradation giving rise to here the double bond and total amine group will be discarded. Whenever double bond will be there, that further treated with this nitrile. When nitrile is treated, that used to generate CH2, CH2, NH2 by this reduction with lithium aluminium hydride. CH2, CH2, NH2, that is chain elongation, homologation, we can say in general. So here the formation of CH2, CH2, NH2 will be originated. This chemistry taken place. Deamination followed by nitrile substitution followed by reduction process accomplished giving rise to CH2, CH2, NH2. Whenever this compound is generated, later we need to treat with dicarbonylic compound. One Ag you can find ester, another Ag you can notice aldehyde. This compound is treated over this one. So here the formation and even tosyl chloride is also one of the substance which is the capping agent, protecting agent. So here upon the nitrogen tosyl group will be added, N tosylated compound will be generated and this is participating in the annihilation reaction. This will react in the cyclization giving rise to pyrrolidine ring with the side chain of ester and being tosyl chloride is a capping agent. Here in tosyl group is also originated. This is the way a new ring system is generated upon this indole moiety. Later, sodium borohydride is the reducing agent. Acetic anhydride is the acylating agent added upon this. When sodium borohydride is added, what it will do? Wherever double bond is present within indole, that will be completely removed and the hydrogen upon the nitrogen and carbon will be generated. This is simply reduction process. Sodium borohydride means further reduction. Acylation, this is the acylating agent so that in acylation carried giving rise to an acylated product. So leaving the entire chemical skeleton unaffected, only the reaction taking place on this nitrogen of indole skeleton. So subsequent ozonolysis. Ozonolysis mean for ozone when added, that used to cleave the double bond position. So if you observe here methoxy, here methoxy, this is somewhat sterically strained one. So here the double bond whichever present, that suitably cleaved upon ozonolysis treatment. So that here the ring opening taking place within the benzene ring, and subsequently ether linkages turned into ester linkages because of that oxygen incorporation. So that here two ester linkages are generated on this benzenoid nucleus. Later on, methanol hydrochloric acid mixture to be added. Whenever methanol hydrochloric acid mixture is added, that's supposed to participate in the ring cyclization with this nitrogen atom. Here we have nitrogen with C double bond O CH3, right? That C double bond O CH3 will participate in ring cyclization with this carbon atom, so that here the six-membered ring, six-membered pyridine ring is originated with ketonic functional. This is a cyclic lactam. Once again, cyclic lactam will be generated with the six-membered nitrogen atom, and leaving this side chain CH2COOMe unaffected. So this remains as is. So here CH2COOMe is also present, but this COOMe is discarded, and this carbon participating in ring cyclization, giving rise to finally a new ring formation. New annihilation will be originated. Now, series of reagents operated upon this one. HI by P. HI by P is meant for what? Hill-Vollard-Zielinski halogenation process will be accomplished. Methanol in the presence of acidified conditions. Again, acylation taking place, sodium ethoxide and methanol. These many reagents combinedly working upon. So wherever N-tosyl is there, that replaced with acylation, being acylation performed, so that in acylation product will be generated. And here we have HI by P, so that alpha iodination taking place in the presence of HI by P, so that alpha iodo ester generation is possible, and that subsequently participate in the ring cyclization. Once again, here the new ring originated. Already we have four rings, tetra cyclo ring system is there. This new ring formation taking place between these two terminal carbon atoms, giving rise to another six-membered ring over there. One five-membered, one six-membered, second six-membered, third six-membered. So this is the way within this molecule you can notice two five-membered ring systems, three six-membered ring systems are located. Later on, tosyl chloride and pyridine. Pyridine working like a solvent and basic medium again, dual role played over there. And here tosyl chloride means for again capping. It is the protecting agent. Wherever free hydroxyl is there, that turned into O-tosyl one. So O-tosyl will be originated. So this is the way kind of transformation you can notice, and this is the kind of molecule generated is one that resembling with this is strychnine. That resembling with this is strychnine. So here certain chemical transformations are further required in order to get ether linkage between these, and ether linkage between these. Another cyclization reaction is also required. Here we have 1, 2, 3, 4, 5 ring systems are there. More one ring system is required to be originated. That subsequent cyclization taking place over there, giving rise to another ring system. This is the way laboratory synthesis of this strychnine will be accomplished, starting with this indole skeleton with the side chain benzene with dimethoxy functionality. These many chemical reactions are operated. It is, if by observing only you can notice it is somewhat complicated synthetic pathway, which is successfully achieved by the scientist called Robert Burns Woodward. This is the way synthesis is accomplished. Here involves 20 plus reaction steps. These many complicated steps are required to be performed, and multiple ring systems to be established within several stereo centers to be observed over there. It is somewhat critical to maintain the reaction pathway in order to achieve the final product, strychnine. Modern synthesis is included. So many reactant species are combining in the stoichiometric ratio within the laboratory, so that here strychnine synthesis is successfully accomplished. These many pathways are established over there. If you observe how many synthesis, how many scientists perform this reaction, wherever complexity is there you can notice after getting the entire burden of doing the work, you will achieve the fruits of that success, right? That's the reason why, though it is complicated, most of the scientists are concerned regarding its synthesis, you can clearly observe. Let me indicate how many type of synthetic pathways are taken directing towards this strychnine as the final product. Here, Cohney accomplished the reaction in the year 1993, starting with an acylated indole with the side chain of secondary amine, inalkylated secondary amine to be taken in either compound alpha beta and saturated aldehyde compound with the two ether linkages. These to be reacted in the systematic pathway, giving rise to strychnine as the final product. Raval is the another scientist who performed the synthesis in the laboratory in the year 1994 by taking one of the compound as benzene fused with dihydropyrrole, and another compound will be a kind of again alpha beta unsaturated when both are supposed to be reacted in the stoichiometric pathway, giving rise to strychnine as the final one. Bosch is the scientist who performed the synthesis in the year 1999, and the World Heart is in successfully achieved this reaction in the year 2000. Shibasaki in the year 2002, chiral asymmetric synthesis successfully achieved for the manufacturing of this strychnine. Lee is the scientist in the year 2002 by taking two ingredients. He got the final product strychnine, and here is the cyclohexane ring with the side chain epoxide and all moiety to be condensed by the scientist called Fukuyama in the year 2002. Chiral asymmetric synthesis accomplished, giving strychnine. And Mori is another scientist successfully performed this reaction in the year 2003. Again, chiral synthesis is accomplished over there, and the Razik in the year 2010 also got the final product as this strychnine. And Van der Waal. Van der Waal is another scientist by taking indole, pyridine, and acetylenic moiety together. Tricomponent system is taken within the single reaction vessel, giving rise to strychnine as the product. In the year 2011, he accomplished this pathway. Woodward is the scientist in the year 1954. It is the starting way of the synthesis, as we already discussed. Fischer-Indole synthesis pathway is taken, and Woodward is the scientist successfully started with this. 1954 is the inception for this reaction, where this strychnine laboratory synthesis accomplished by taking in phenyl hydrazine, one of the component, and either ester linkage, either is a kind of benzaldehyde analog. So this is the way strychnine formation is possible, and you can achieve the same reaction by taking this polyannular system and in either is a cyclopentene system by the scientist called Overman in the year 1993. So these many reaction pathways are able to direct the entire pathway towards the synthesis of strychnine. This is the way asymmetric chiral synthesis of strychnine is accomplished by various scientists. They are successfully achieved this final product. By this, we conclude this laboratory pathway. Let me introduce their properties. Being it is the solid one, except nicotine, all the alkaloids are solids only. So here, white crystalline solid is the nature for this compound, extremely bitter taste because of more nitrogen atoms within the molecule. Slightly soluble in water, being it is organic entity, so that most organic flavor will render the water solubility, and is soluble obviously in the alcohol and chloroform because of its organic nature. Much more carbon content is retrieved within the molecule. That's the reason why solubility in the organic solvents are more common. And a chemical nature, it is accomplished with the nitrogen with the tertiary amine, and either tertiary amine is there. So that tertiary amines obviously weakly basic in nature because of the stereochemistry plays a dominating role over there. That's the reason why hydrochloric acid, when treated tertiary nitrogen totally occupied by the surrounding alkyl groups only. That's the reason why lone pairs are not suitably available for the neutralization with this acid, so that neutralization is possible, but the extent of reaction will be somewhat less. Product formation is somewhat less in comparison to the primary and secondary amine. That's the reason why strychnine is a weakly basic in nature. Salts with acids are possible, but the extent of salt formation percentage of yield will be somewhat low. Optically active, all the carbons, you can notice where the carbons are optically active. Here is the carbon which is optically active in nature. Here is the carbon you can notice optically active. Here is the carbon optically active. Here is the carbon not optically active. So one carbon here, one carbon atom, two carbon atoms, three carbon atoms, four carbon atoms, five carbon atoms. 1, 2, 3, 4, 5, 6 carbon atoms are chiral carbon atoms located within the strychnine molecule. That's the reason why it is optically active in nature. If you go with their chemical properties and reactivity, basicity, being tertiary amine is weakly basic, so that weakly basic nature is adopted by this compound, and the mineral acids are sufficient to make the salts with this one. Oxidation is also possible. Strychnine derivatives are possible. Strychnine derivatives are generated wherever ketonic moiety is present. This strychnine derivative formation taking place with this ketonic functionality. Oxidation, strychnine derivatives will be originated if you treat with chromic oxide, water generates a chromic acid H2CrO4. So let me carefully indicate the structure. So entire strychnine is complicated when that's the reason why the suitable part, the suitable fragment whichever required for the oxidation to be taken into the consideration over here. Here you can notice the 7-membered ring, right? The 7-membered ring, only the susceptible moiety where the oxidation is more preferential. This chromic acid is the kind of strong oxidizing agent operated over there. So here the bond formation between the chromium and the 7-membered ring carbon atom, and that able to form a kind of chromate ester generation is possible, that will further participate in removal of this chromate moiety, and this olefinic double bond is moving towards the side, lone pair of electrons and the nitrogen back polarized over there, so that here the kind of conjugated system is located, and the chromium fragment will be discarded, and water will be added upon this molecule. Whenever water is added, there is a hydroxylation taking place, and the adjacent carbon atom again chromic acid to be treated, right? Whenever chromic acid another mole molecule is treated, here hydroxyl will be transformed into ketonic one. So whenever ketonic one is generated, let me treat with another mole of chromic acid, so that here again the formation of bond with this carbon atom, and here the formation of new pi bond between the carbon-carbon, and this ketonic pi bond is polarized toward the oxygen, giving rise to oxide. Later, within the molecule, rearrangement taking place, back polarization of negative charge toward the side, here the ketonic form generation, and wherever double bond is there, the double bond is participating in the reaction with oxygen, leaving the chromate moiety, and here is the epoxidation. So epoxidation taking between, so here you can notice the 3-membered ring with the oxygen hetero atom. Epoxide, whichever generated, again highly sterically strained, right? So 3-membered ring with the oxygen is highly unstable one. So that one more molecule of chromic acid to be treated. So here oxygen is going to work upon this carbon atom, and the bonded electrons are moving towards the oxygen, and oxygen susceptible for protonation by acidic conditions. So that here you can notice the hydroxyl, here you can notice the chromate ester. Later, again the rearrangement taking place, bond delocalization, cleavage, and making is possible. The OH group is discarding this hydrogen, and here again ketonic moiety is originated. Whenever this is forming a ketonic group, here ring opening reaction, being adjacent oxygen atoms are highly sterically strained, because lone pair repulsions are most predominated, which able to cleave the bond, which able to cleave the ring system, so that here the diketonic moiety is generated, and the chromate moiety is again removed. Whichever generated is vicinal diketonic one. Here you can notice the kind of aldehydic functionality at the at the terminal carbon atom. Whichever terminal carbon is there, that turned into aldehydic functionality. Let me treat one more chromic acid molecule. So chromic acid will not affect these diketonic moiety. Rather, aldehyde group is more reactive towards this oxidation and subsequent higher oxidation state, that is carboxylic acid. This is the way carboxylic acid will be generated in between. And here these two carbons also converted into oxidized form called a ketone. These many kind of oxidized points will be originated by this strychnine oxidation. This is the way strychnine oxidation reaction is performed. Strychnine taken initially. Wherever this 7-membered ring is there, this is 7-membered ring is more preferable for this oxidation process. This totally ring opening reaction is possible, and wherever this nitrogen adjacent carbon atoms are there, these two carbons are converted into diketonic, and this carbon turned into aldehydic one. So oxidized product will be originated. This is the way the mechanism followed by the chromic acid oxidation under acidified conditions. Now let me perform the strychnine reduction. Reduction taking place between palladium and hydrogen. Strychnine is the polyannular complex system to be reduced in the presence of palladium hydrogen. Where the reduction taking place, let me observe. The entire molecule is said to be saturated except this double bond, so that this double bond only suitable for the reduction, leaving this benzene unaffected. Being it is aromatic, will not be affected by simple reduction process. Rather, this double bond is isolated one ring. No conjugation, no aromaticity, nothing is there. That's why it is susceptible for reduction process, so that it is conveniently reduced. So the dihydrostrychnine is the final product. This is about the reduction in the presence of palladium. Let me perform hydrolysis. Strychnine is rigid towards hydrolysis reaction. It will not work upon this hydrolysis, so that the reaction is hindered. So resistant towards the hydrolysis because of the rigid structure. More complicated annulation is involved within the molecule. That's why it is not operated with this hydrolysis process. By this, entire chemical properties are discussed in detailed manner with the mechanism and with the brief explanation as well. Let me conclude the session by introducing their applications. Applications in the field of medicinal use, right? Medicinal use is historical in nature. The molecule called strychnine is a central nervous system stimulant, able to activate the nervous system. And paralysis kind of diseases will be effectively curated by means of strychnine. The people who are suffering with partial paralysis, like one leg or else entire one side body part, or else two hands, or else two legs, or else entire body except head. So this is the way multiple kind of paralysis the people who are suffering with effectively curated by means of the drug called strychnine, right? Here, strychnine and brucine together are very essential. The people who are suffering with this weakness. So these are effective medications. So strychnine, brucine together extracted from the same plant, Strychnus nuxvomica, right? And the modern uses of this strychnine included with research tool, it will be. Within the research, it is efficient one, neurobiology. So here, in order to go for the extensive research regarding neurological functioning, this kind of strychnine is the efficient pharmacophore, right? Glycine and receptor antagonist. Glycine receptor antagonist is nothing but glycine is the kind of amino acid, right? Antagonist means it used to suppress the secretion of that glycine. So that is the way neurobiology operation will be performed by this strychnine. Used in toxicological studies, the any kind of poisonous conditions, any kind of hazardous conditions, toxic studies you are performing with this strychnine is an efficient tool in order to operate with them. In addition to this, other uses also there. Rodenticide. Rodenticide is nothing but within the farmlands, croplands, grain grain quality will be disturbed, and grain what injury is possible by means of these rodents like mouse and also kind of insects. So all these will be restricted by means of strychnine because of its toxicity. It works like a rodenticide. You can use it as a rodenticide. It used to kill the mouse in the croplands, wherever grain storage godowns will be there, there also we require to work with this what grain quality, right? So there you can use this strychnine as a rodenticide, right? How this rodenticide activity will be performed? By blocking this glycine receptor within that rodents, within those mouses. For the strychnine used to work upon that glycine receptor, so that glycine secretion will be blocked, so that protein synthesis may not be possible. This is the way it works on the rodenticidal activity, right? Pesticidal activity, we can clearly say. And in the spinal cord, central nervous system activation is possible. Paralysis conditions will be effectively curated uh, because uncontrolled nerve stimulation is possible by the consumption of this strychnine, so that we efficiently curate this paralysis disease. It is a neurological stimulating agent. So by this, we are successfully concluding the session, where the structurally complex, biologically potent indole alkaloid, it will be immense applications are noticed in the medicinal field. Organic synthesis, it is the efficient lead compound for the synthesis of new chemical entities, and in the neurochemistry it works well, and neuro research also, it is like a standard compound. Alkaloid biosynthesis, you can add to this strychnine, and despite the toxicity, remains a landmark compound in the history of organic chemistry. It also contains a toxic effect. That's the reason why it works like an efficient rodenticide. Apart from that, it is the potent medicine as well. This is the way the entire concepts regarding strychnine were completed. All are available at the channel called World of Competitive Chemistry. If you are preparing for any competitive chemistry, you can add to this channel. You can subscribe the channel so that you can get multiple series of sessions which give the extensive information regarding the chemistry. Thank you, one and all. Thank you for your patient listening.